start the recording now. It is still very rainy and windy here. So what are we going to do today? I don't have an official 6033 news segment for you right now. But one thing I do want to note, over the past week, I learned about this from Karen, so thank you, Karen. There were some DDoS attacks on the CSAIL mailing lists. If any of you are on any of the CSAIL mailing lists, you may have noticed that you weren't getting very much mail from them. We are going to talk about that in a couple weeks, so just sort of know that that happened and it'll come up again. It was sort of an interesting style of attack in a way. So where are we? So this is where I left you last time. We've talked a lot about atomicity, and we've basically got it working for a single user on one machine via logging. Right? Logging, overall performs quite well, especially as we introduce cell storage and we introduce a cache. Adds some complexity compared to something like shadow copies, but overall, this is how we're going to achieve atomicity. And so today we are ready to move on to isolation, which we don't really have yet. So what we're going to do today, we are going to provide isolation in the context of still a single machine, but now you can imagine multiple users. And we're going to do this via a protocol known as two-phase locking. But the way this lecture is going to work, we're going to spend really about the first half of the lecture talking about what we even want when we talk about isolation, because as it's going to turn out, there are a lot of different ways that we could kind of define things here. So we're not actually going to get to two-phase locking until really the second half of this lecture. All right, but the goal here is to get an understanding of what might happen as we run transactions concurrently. This is going to be useful if things fail for sure, but this is actually a useful thing to reason about even when things aren't failing. All right, so what is our goal going to be? Here is our goal within the context of this lecture. All right, and at the beginning, it's not going to be a well-defined goal. All right, and we'll talk about why. All right, so we're going to think about a system where we have n transactions that we need to run concurrently. And for us today, we want it to appear as if they ran sequentially. All right, so let me talk a little bit about what that might mean. All right, and I'm going to make this really concrete for us. We're going to look at these two transactions for basically this entire lecture. Let me talk a little bit about syntax here, just so you have a sense. So we have two transactions, T1 and T2. I've given them line numbers, right? So like these things here, those are just line numbers. They're not part of the actual transaction. I just want to be able to refer to like line 1 of T1, line 1 of T2, etc. And you can see, we're doing some reads and some writes of two variables, X and Y. This is effectively the same syntax that we've been working with. The only thing I did here explicitly in T1, I called out this read separately in its own line, just to make things a little bit clearer for today's lecture. So these are the two transactions we're going to work with. And when we run them concurrently, we're always going to run the steps of a transaction in order. So like T1.1 is always going to come before T1.2. That's always going to come before T1.3. But we might interleave the other transaction, right? So I might run like line T1.1, then T1.2, and then maybe I run the first line of T2 in the middle, right? You will see so many examples of possible schedules. You will be sick of examples of schedules, right? But that's what we mean when we run them concurrently. And so, okay, we're gonna have it appear as if things, ran sequentially. One option certainly would be to just run our transactions sequentially, right? Run T1 and then run T2, or run T2 to completion and then run T1, right? This is something that we could achieve with, say, a single global lock. All right, it's the style of concurrency we would see if we were back to talking about locks and we were talking about coarse-grained locking, right? It would give us a lot of, potentially nice properties in terms of reason about concurrency, but that's at the cost of so much performance, right? We wouldn't actually be doing anything concurrently. I saw these messages in the chat and I thought there were so many questions, and I see everybody's doing a really great job of telling me where the rain is. The rain in Malden has stopped, but please keep up with these reports. This is very fun. Okay, so we don't want to do this. We don't want to just run transactions sequentially, all right? So we need to dive into this goal a little bit more, because what does this even mean, right? What does it mean to appear as if two transactions ran sequentially, right? The first thing we're gonna do, we're gonna kind of examine a few different schedules, right? And we're gonna compare them in a couple of ways to what it is like when we run these transactions in sequence, all right? So I'm changing our goal here just a little bit because we are focused on T1 and T2, right? Since we're interested in, a comparison to what it's like to run them sequentially, so that's T1 before T2 or T2 before T1, let's just understand what would that be like, right? What happens if I run all of T1 and then I run all of T2, right? So you can, oh, spoilers. We can go through this, right? So we're gonna do, some reads of X, a read of Y, right? Here, we would end up writing 10 to Y. We're gonna see X and Y are initialized to 0, right? And then we would go and write 20 to X, right? 30 to Y. Right, so, at least at first, here's one result. And right now, we're just looking at what the final state of these two variables is. That's one way to get a sense of what's happening here. All right, so if I run T1 and then run T2, here's my final values of X and Y. Right, now, if I run it the other way, I get a different result, right? Because T2 does its writes, right? X equals 20, Y equals 30. T1 does a read of X and does a read of Y and adds 10 to Y. All right, so, whether I run T1 before T2 or T2 before T1, I get two different results. That's okay. All right, for our purposes, we don't have any problem with that. Right, the reason we're looking at this is because we're just trying to get a sense of what a sequential schedule of these transactions would do so that we can look at some more interleaved schedules and kind of compare. All right, so let's look at that, right? Let's look at some options that don't have these transactions run serially. Our goal is going to be to decide, eventually our goal is to decide like whether any of these schedules are they allowed? Like, are they allowed for the particular type of isolation we want to achieve? But for now, we're just getting to know them. Okay, we're just exploring some possibilities. So we're going to look at these three other schedules. All right. So here they are. There's in some ways just like random interleavings of T1 and T2. They're not random in the sense that I selected them for like particular pedagogical purposes, but just here are some schedules, right? Let's do the same thing. Looking at these schedules, let's just ask ourselves, okay, what would the final result of X and Y be after we run these? Let's just try to understand, are we always going to get like one of the top two results, right? Are we always going to get something that looks like this? Could we get something different? Right, let's find out. All right, so if we look at this first schedule on the left, right, you can see we do a write to 20 of X, then there's a read, a write to 30 of Y, then we'll end up reading Y and adding 10 to it. All right, so we would end up with X equals 20, Y equals 40, which, okay, that's worth noting. This result here, it's the same as one of our sequential schedules. That's fine. All right, let's do the next one. All right, so we're going to see something a little bit more interesting happen here. All right, T1 reads X equals 0. T2 comes in and writes X equals 20. Then we go back to T1, we're reading Y equals 0. All right, and then T2 writes Y equals 30. And then this final rate of Y, though, is going to write Y equal to 10. Right, and again, it's because T1 read that previous value of Y. Right, so we end up with this result. Okay, that's curious. That's not equivalent to either of our sequential schedules, right? Again, we're just getting to know the schedules. Then we do the same thing with the last one, right? And you'll find we end up with this again, right? We do our write 20 and 30 to X and Y, and then we end up incrementing Y by 10. So if we're living in a world where we're trying to look at these schedules and say, okay, are any of these schedules, do they have the same effects as if we ran things sequentially? It sure seems like the middle schedule is kind of out. All right, this final state this final written state of X and Y, it's not possible in either of our serialized schedules, our sequential schedules, right? We don't see X equals 20, Y equals 10 here. So, okay, this schedule, it seems like it's not going to be equivalent. But the other two have the same final state, so let's investigate a little bit more. All right, and in particular, I want us to look at this one all the way on the right, this third schedule here. The final state of these two variables, X equals 20, Y equals 40. That's exactly what we see if we run T2 first and then T1 first. But there's some stuff that happens in the middle, right? In this first step, T1 would read X equals 0. Then we run T2. Then the second step of T1 would read Y equals 30. Okay. Those reads together, they aren't possible in either of these sequential schedules, right? If you look at our schedule, our sequential schedule over here, those two reads that T1 does, it gets X equals 0, it gets Y equals 0. If you look at our schedule here on the right, T1 gets X equals 20, Y equals 30, right? But here, it's getting X equals 0 and Y equals 30. Is this okay, right? What do we want, right? Do we care only that the final written state is equivalent to one of the sequential schedules? Do we care about these intermittent reads, right? It's a good question. And the answer is that it depends. We might care, we might not, right? There are many ways for a sequence of transactions to appear to have been run in sequence. The word we're going to start using for this is there are different notions of serializability. And what type of serializability you want depends on what your application needs. To give you some words for what we just did, if you only care about the final written state of your variables, you don't care about those intermittent reads, we would refer to that as final state serializability. Right, but we're going to spend most of the time today in lecture talking about a different style of serializability, right? And in going through this, we're going to find that schedule all the way on the right with these reads is not going to be allowed under this particular style of serializability. All right, so let's do it. The type of serializability we're going to spend a lot of time on in lecture is known as conflict serializability. And so before I can talk to you about conflict serializability, you need to know what a conflict is, right? So same two transactions. These are going to be the same two transactions for all of today. All right, so two operations conflict if they operate on the same object, so like the same variable. So in this case, X, they're both operating on X or they're both operating on Y. And at least one of those operations is a right. So what we're first going to do is we're going to look at these two transactions, T1 and T2, and we're going to try to decide across these transactions what operations conflict, right? What are the conflicts? So I will show you one. And the way that a way to do this is to literally just say, okay, I'm going to start on the first line of T1. It's a read of X, right? What lines of T2 would conflict with that, right? They would have to be operating on X, right? And they'd have to be a right, because this is a read. And so indeed, that first read of X, right, it conflicts with this right, right? Because again, they're operating on the same object. They're both operating on the variable X, and at least one of them is a right. Okay? There are other conflicts between these two transactions. All right. Here's the second one. We do a read of Y over on the T1 side. That's going to conflict with a right of Y in T2. All right. Similarly, we do a right of Y in T1. It's going to conflict with a right of Y in T2. Right. So why are we defining a conflict this way? Here is how I think about it. When we're thinking about concurrency, And you can go back to operating systems if you want. Like you can think about threads, that's fine. You don't have to think about this in terms of transactions. The thing that is problematic is if you have two processes that are both accessing the same variable, and at least one of them is trying to change it, right? If I have two processes and they're interacting on entirely separate sets of data, who cares? Who cares how I interleave them? It doesn't matter. They're not going to damage each other. If I have two processes and they're just doing like a million repeated reads of, say, a variable X, but neither one of them is changing it, okay, also, who cares? Who cares how I schedule those together? Nothing's going to change. Problems occur if I have this thread running that's reading X and this thread running that's writing X, or two threads running that are both writing to X. All right. So this notion of a conflict is in some saying, okay, the thing that matters is if one of our transactions is writing to a variable and other transactions are also trying to do something with that variable. That's what's going to matter here. All right. So now that we know what a conflict is, right, now we can talk about what it means to be conflict. Well, we cannot yet talk about what it means to be conflict serializable. We are one step away from being able to talk about that. Now we have these conflicts. Here's the next fun thing that we can do. We can look at particular schedules. This definition is going to seem like a lot. We're going to do 4 different examples, so I got you. All right. If we look at a particular schedule, we can say, okay, you know, these operations that conflict with each other, they're going to come about in some order, right? Either A goes before B or B goes before A. And we're going to talk about that as the order of the conflict, right? So let's do it. Suppose this is my schedule, right? I'm running T1 to completion and then I'm running T2. Right, I have my conflicts here at the top, right? We found these conflicts from before. So we're just gonna ask, I pointed to it over here as if you all could see that. We have these conflicts here at the top. We're gonna look at each one of them and say, okay, in this schedule, which operation comes first? Right, so for instance, we'll look at this first conflict, right? Between T1.1 and T2.1. In this schedule, T1.1 is executed first. It comes before T2.1 in the schedule, right? So there's the order there. And we can keep doing them. I did not mean to reveal all of this to you at once, but here we are. Right, we can keep doing this. And this is not super surprising in this particular schedule. I ran all of T1 before any of T2, right? So in all of these conflicts, whatever T1 does, it happened before T2. Right, so here are the order of conflicts. We haven't done anything with this. This is just you're getting to know these particular schedules really, really well. We're going to do something with this in a second. To keep the slides more reasonable, because I am repeating the lines of T1 and T2 in a lot of places here. I'm going to change this notation a little bit. So we're just going to write it like this. All right, so let's do this again. All right, there's a lot going on here. We are going to practice this 3 more times. All right, suppose we did, our second schedule. We're going to run T2 to completion, and then we're going to run T1. All right, I'm going to give you all, you don't have to answer anything. You don't have to answer a poll. You don't even have to put anything in the chat. Take 30 seconds. Think about these conflicts. What is the order of each conflict? Okay, so you think it to yourself. I'll count to 30 and then we'll come back. Okay, I've counted to 30. If you're a person who ever wants to go into teaching, let me tell you that one of the best skills you can get for yourself is an ability to wait awkwardly through at least 10 seconds of silence. So as you can see, I can go to 30. I'm very good. So, all right, let's look at these. In our first conflict, T1.1 and T2.1, T2.1 comes first, right? And again, it's literally, it's first in the schedule. That's all we're asking here, right? So subsequent conflicts, again, not super surprising. We ran T2 entirely before T1. And so notice that if you're executing things in sequence, you're either going to see, all of T1's operations occurring first or all of T2's operations occurring first in these conflicts. The order of your conflicts is going to be the same for every conflict. So let's do something more interesting. Let's try this on a schedule where we're mixing things up, right? What are the order of our conflicts like now? All right, well, in the first one, T1.1 and T2.1, right? We can see that T2.1 executes first, right? It comes first. All right, T1.2 and T2.2, all right? It happens that T2.2 comes first. Similarly with the last one. All right, so it's kind of interesting. We have this interleaved schedule, but yet, it happened here that in all of the conflicts, T2's operation occurred first. Interesting enough, does that always happen? Let's find out. All right, here's another example. Arguably the most exciting example. All right, same thing. We're going to look at every conflict. There's 3 of them, and we're just going to ask ourselves, okay, what operation comes first, right? T1.1 occurs before T2.1 in the schedule. All right, but twist, in the second conflict, right, this conflict here, T2.2 comes first before T1.2. Right, and the same with our last one, T2's operation comes first. All right, what are we going to do with this? All right, you can see on the left schedule, the order of the conflicts is the same as if we had run T2 entirely before T1. All right, on the right, the order of conflicts isn't the same as either serial schedule. It's either like sequential schedule. I use those terms interchangeably. I'll try to be better about not doing that. All right. This is the thing we're going to care about when it comes to conflict serializability. The reason we went through this exercise in so much detail is because a schedule is conflict serializable if the order of its conflicts is the same as the order of its conflicts in one of the sequential schedules, right? That means in this example, if we get a schedule where the order is either always T1's operations before T2 or always T2's operations before T1, right, then we are good to go. So this schedule is conflict serializable. The conflicts are ordered in the same way they would have been ordered if we had run T2 first and then T1. This schedule on the right, it's not conflict serializable, all right, because we see, we see this switch, right? In one, we have T1's operation and then T2's, another we have T2's and then T1's. So the order of these conflicts really matters in assessing whether a schedule is conflict serializable. Notice that I have not given you a way yet to actually generate conflict serializable schedules. We're going to come to that. We're still sort of given this problem of like, here is a schedule. Is it conflict serializable? So one of the ways you can do this now, find all the conflicts, look at the order of the conflicts, and decide if they are equivalent to the order in a serial schedule. But let me give you what is at first going to seem like more work, but in the end will make your life easier. We can represent these conflicts in a slightly different way. All right, I'm going to put a definition on the slide. It's going to seem like a lot. Don't worry. We're going to make a conflict graph. All right, conflict graphs are really fun if you like graphs. If you don't like graphs, they're still fun. All right, so in our conflict graphs, the nodes are the transactions. All right, so here I will draw them for you at the bottom, but then we'll put them on the slide meter. Okay, these are our nodes. We just have T1 and T2. We'll do a more complicated one at the end of lecture. Right now we're going for the basics. Right, so we can draw a conflict graph for both of these schedules. Right, there's going to be an edge between two transactions if they have a conflict, right? And the direction of that edge, it's a directed graph, is going to indicate the order, right? So like, let's do it. We're just going to do it together. All right, so we have 3 conflicts here on our first schedule. In the first one, T2's operation is before T1s. So we would draw an arrow between T2 and T1. From T2 to T1, sorry, the direction is important. And we would keep doing this, but we'd be drawing the same arrow, right? This is the conflict graph for this schedule, right? It just says, okay, from T1 to T2. The conflict graph for the next schedule is a little bit more interesting, right? Because we get to draw two arrows, right? The first conflict you see here is between T1 and T2, but T1 comes first. So we get to draw an arrow in this direction. That second conflict from T2 to T1, all right? Right, we get to be here, right? The note, yes, the nodes are not the steps in the transactions, they are the transactions, right? So this is literally the transaction T, that's a terrible circle, the transaction T1, right? Not like T1.1 or T1.2 or anything like that, right? So here are my drawn conflict graphs. Let me put them for you on the slide. I see that I've chosen to put T2 on the left here, which is a fun choice. All right, so here are our conflict graphs. They're not particularly exciting for these two schedules because we only have two transactions. We only have two nodes. Like I said, we'll look at a slightly more complicated case at the end of lecture. But what is useful about this? What is useful about this representation? Well, you know, it's a little bit more succinct, right? But more than that, a schedule is conflict serializable if and only if it has an acyclic conflict graph. Right, so an acyclic conflict graph, it means a graph with no cycles, right? So this graph over here, it has no cycles, no loops through the graph. But this one over here has a cycle, right? T1 to T2 and then back to T1, or if you prefer T2 to T1 and then back to T2, right? So this is another way for us to say, okay, this schedule on the left, it's not conflict serializable, right? And again, this graph, this style of expressing conflicts, it's going to be helpful when we have more than two transactions. Like it gets more helpful the more transactions you have. Okay, so at this point, you know a lot about these example transactions and the possible schedules, right? So our goal, our real goal, is to run these transactions concurrently, but to produce a schedule that is conflict serializable. How do we do that? How would a system do that, right? Like I said, all the problem we've been tackling so far has really been, here's a schedule, decide if it's conflict serializable, right? So you can imagine a system, it takes its transactions, it looks at all the schedules, it looks at all the conflict graphs, it finds the ones that are acyclic, and it picks one of those. But that's kind of a lot. That's just a lot, right? So what we are going to do, we're bringing back locks, right? And we're going to apply them in a systematic way, all right? So we are going to apply them via a protocol called two-phase locking, which we virtually always abbreviate 2PL, all right? I am going to show you the protocol. I am going to show you an example of the protocol being used. And if you are really, really into this, you might notice that our first take on the protocol, it's going to have some challenges. There's going to be some issues with performance. There's even going to be some issues with deadlock. Okay, we are going to address those. Let me just present the protocol to you all first. So don't panic if you are thinking about this and you feel like something's not quite right. All right, so here's the basic protocol. Despite the fact that it involves locks, it's a soothing protocol, I would say, right? Every shared variable is going to have a lock. This means that we're using fine-grained locking. So in the context of our transactions, there's going to be a lock for X and a lock for Y. All right, so every variable gets a lock. If you want to do anything with a variable, you need to hold the lock. So that seems fair. All right, so at this phase, if we're going to read X, if we're going to write X, we need to first acquire X's lock. All right, nothing super surprising so far. Step 3 is the crux of this. Once a transaction releases a lock, it can't acquire any other locks. This is why the protocol is known as two-phase locking. You have a phase in which a transaction is acquiring locks, and then a phase in which it's releasing locks. right? So let's see, this is it. This is the protocol. It still gives us kind of some options, all right? So we're gonna just look at T1. Don't worry about T2 for now. T1 is all we care about at the moment, all right? Here's one way we could apply locks that would be a valid two-phase locking protocol, right? T1 is dealing with both X and Y, so it needs locks on both X and Y. So, it could just acquire both of them at the top and release both of them at the bottom. That is fully adherent to two-phase locking. It could also do this. It could say, oh, I'm gonna, acquire that lock right before I need the variable, right? That's also fine as long as it doesn't release a lock in between. That still adheres to what I've set up here. We could even, release one of those locks earlier, right? At this point in this transaction, we're done with X. We could release X.lock there, right? And then wait and release Y.lock, right? All of these, there's trade-offs to kind of all of these approaches, but all of these are valid. Here's the one that's not valid. You can't do this. This breaks the third rule of two-phase locking, right? As you can see, we have like an acquire and then a release and then another acquire. You can't do that, right? Your acquire and your release phases, they can't overlap like that. There has to be a clean break, which we call the lock point. All right. So a common way that you might see this happen, it's really common to see two-phase locking work in a way where we don't release the locks until after the commit point. Until after the transaction commits. This is a slightly different version of two-phase locking, strict two-phase locking. If after this lecture, you go to the Wikipedia page on two-phase locking, there are so many versions, you will be overwhelmed by the number of slightly different ways to do two-phase locking. All right, so there are a couple of things that we need to address here. There are some lingering issues, some related to deadlock, which I'll give you an example of, some related to performance. For instance, in these two transactions, if I apply two-phase locking the way I have here, it's just gonna run them serially, right? They both start by trying to get a lock for X. They hold the lock until the end of the transaction. They're not gonna actually run concurrently. We're gonna come back to all of that. Okay, we're going to address that. But before that, I wanna try to convince you that this works, right? I want to convince you that two-phase locking produces a schedule that is conflict serializable, okay? First, I'll be really careful about that claim. Two-phase locking does not produce every possible conflict serializable schedule. Even if you go through all of the different places you could do your acquires and release, you're not guaranteed to get every possible schedule. What you're guaranteed is that the schedule you do get will be conflict serializable. So I'm going to do a proof for you, all right? And what I want you to know about this proof, it is important to me that you understand that two-phase locking works and you understand why it's correct. But we would never expect you to recreate this proof on an exam, right? We are not expecting you to do these types of proofs. But I have structured it in a way that I hope will be pretty intuitive, that will help you understand why this approach to locking works. Also, I personally think this is really cool, that you can think about what feels like such a systems issue. Like, my goodness, we're doing locks, we're thinking of transactions, we're kind of like in a database, and yet it has this really nice theoretical background. I just think that's very neat, all right? So here's our proof. I'm gonna prove to you that two-phase locking produces a conflict serializable schedule. A different way to say that would be it produces a conflict graph without a cycle, right? An acyclic conflict graph. Okay, we will prove this by contradiction. So suppose not, right? Suppose it didn't. Suppose you did two-phase locking and you got yourself a schedule that had a conflict graph with a cycle. All right, let's see what that might look like. This is how we're going to talk about the cycle. Cycles don't have to be just between two nodes. They can be between, up to k nodes. So here's an example of a cycle, right? So this says T1 had a conflict with T2, right? And T2 had a conflict with T3, T3 had a conflict with T4, et cetera, all the way back to TK, then having a conflict with T1. All right. Now, how does a conflict come about, right? A conflict comes about if two transactions are operating on a shared variable, right? If they're both operating on X, or they're both operating on Y, or they're both operating on Z, or whatever, right? So there had to be some shared variable here, right? I'm going to name them X1, X2, X3, all the way up to Xk. Right? So what I mean by this is, okay, we know that there is a conflict between T1 and T2 because there is an edge between them in this graph, all right? And we're just gonna say, okay, well, whatever variable they conflicted on, call it X1, all right? Similarly, there's a conflict between T2 and T3. Whatever variable they conflicted on, call it X2, that's fine, right? So now, how does this come about in two-phase locking, right? Well, in the schedule, right? Each shared variable has a lock. So X1 has a lock, X2 has a lock, X3 has a lock. All of these shared variables, they have to have locks, right? That is rule number 1, right? Rule number 2 is that, well, if a transaction is going to do anything with them, they have to acquire the lock. So this schedule would start to look like this. There could be other stuff going on in between. All I care about is the acquires and the releases, right? So T1 has to get a lock on X1. And then sometime after that, T2 gets this lock on X1, right? Similarly, T2's got to get a lock on X2. And then after it, T3 gets a lock on X2, right? All the way up to TK getting a lock on XK, and then T1 getting a lock on XK. Because remember, an edge in the graph means that these two transactions both did an operation with that shared variable. In order to do that operation, they had to acquire the lock. And we even know something about the order in which they acquired those locks, because we know the order of the conflicts, right? And again, all sorts of other stuff could have happened in the middle here. I don't care. I only care about these acquisitions. Okay, now this is looking fine. This is great. For this schedule to have progressed though, T1 had to give up this lock on X1 at some point, right? T1 acquires a lock on X1, and then T2 later acquires it. So somewhere in between those, there had to be a release, right? And it, same thing about X2 and X3 and all, but we really care about X1. And the reason we care about X1 is because that is kind of the focal point of our cycle, all right? Because if T1 has released a lock up here, notice that it later acquired a lock at the end. This is not allowed. This is not a schedule that comes about via two-phase locking. You are not allowed to acquire after you release, right? So to be clear, everything was actually fine. It would be fine for T1 to have done this, acquired X1.lock and then released it, and then other transactions could come in and do their thing. The problem is that down here, T1 acquired another lock. It's not allowed. That's step 3 of the protocol. All right. So if you have a cycle in your conflict graph, you had to do something like this, right? You acquired a lock, you released a lock, and then you acquired another lock later on. Right, so that is how we know that this protocol works. And again, we're not going to expect you to recreate this proof, right? But I don't like to present two-phase locking and just say well, just trust me, it produces a conflict serializable schedule, right? Now you can trust me, but also there's math, right? So let's look at some of the points of concern, all right? I'm gonna keep the protocol on this slide. We're gonna go back to our 2 transactions. And again, I have one example of how we might do two-phase locking here, right? Now, suppose that these transactions were a little bit different, right? Suppose that in T2, I'm just gonna swap those 2 rates, right? I'm gonna do my, excuse me, my right to Y before my right to X. You will have seen an example like this before. You've seen this when we were back in lecture 4, we were moving files between directories. You can imagine what would happen here, right? T1 gets X.lock, and then T2 gets Y.lock, and then they can't make any progress, right? This is the exact same example we had when we were in operating systems, right? And we came up with a very unsatisfying solution, which is global ordering unlocks, right? But we don't like that. It's messy, it's not modular, right? Here's an alternate solution that you now have. You can give up, right? If your two transactions have deadlock, you can just stop one of them, abort one of them, take advantage of atomicity. It'll roll itself back. Everything will be fine, right? This, in many ways, I think is actually quite elegant. You don't have to worry about a global ordering. You have all of this atomicity built in. You can just stop one of the transactions, right? Abort it. Now, you would have a different problem, right? How do you detect whether two transactions are actually deadlocked? There are multiple ways that a system might choose to do this. You can determine whether two transactions have the potential to deadlock by creating something known as a weight dependency graph. It's not unlike a conflict graph, right? It's sort of, but it shows you a relationship between locks, right? Not between conflicts. And if there is a cycle in your weight dependency graph, then you can result in deadlock. We're not going to make weight dependency graphs. You all have enough graphs happening already. We don't need to do that. So that is certainly one way you can do this. It requires some bookkeeping. Other systems will take maybe just a different approach and just say, if a transaction is running for, if two transactions are running for more than some amount of time, right? Again, just abort one of them at some point so that the other one could go on. It sort of assumes that you have deadlock if two transactions are running for a long time. And that's a parameter that you could tune for your system. So there are different approaches, but there are ways to do this in practice. All right, so we can deal with the deadlock problem. The second issue I want to bring up is some issues of performance. All right, and people who think about two-phase locking a lot think a lot about performance. Right, I'm just going to give you sort of one performance optimization. It's a slightly different style of two-phase locking. I like thinking about it because I think it sort of meshes really well with our thinking about conflicts, right? Because again, let's think about how we got to conflicts. We recognized that problems can occur when one transaction, one process, one thread, whatever, is writing to a variable, and other transactions, processes, threads are trying to also do something with that variable, right? But if we're just doing a lot of concurrent reads of a variable, things are fine, all right? So a different approach to two-phase locking, which it's basically the same with some extra details. We're gonna allow for reader and writer locks. So the way that works, now each shared variable actually has two locks, one for reading, one for writing, right? You still have to acquire the appropriate lock on a variable before you try to access the variable. If you're trying to read X, you need to get X's reader lock. If you're trying to write to X, you need to get X's writer lock, right? But now you are allowed to have multiple transactions reading at the same time. That is allowed, right? Writers, once someone's trying to write though, it's got to wait for all of the other locks to go away, all right? And then the last rule of two-phase locking is still there, right? So again, I'll give you an example here of these two transactions. It looks a lot different. It's partly because I had to move from like x.lock to just x.readerlock or y.readerlock, right? So you can see how this might look, all right? In practice, we'll actually see read locks being released earlier, right? So this is something we would see in practice. So this is just a small optimization to allow for multiple concurrent reads. There are some issues of fairness. I'll call this out in the notes just for those of you who are interested. You wouldn't want, a ton of reads to kind of block the process of ever writing to a variable. There are some ways around that. All right, so this is not without fault, but this is just a common sort of optimization that we might see in practice. There are all sorts of other small changes that you can make to two-phase locking, right? There's a ton of trade-offs between exactly how this protocol works and performance. But the last thing I kind of want you to take away from this lecture is that another way to think about performance here would be to give up on conflict serializability entirely. Conflict serializability is a pretty constrained form of isolation. There are a lot of schedules that it does not allow. All right, we could be more relaxed about this. So let me give you one last example, and it's blank because I'm going to draw it for you. All right, so we're going to have 3 transactions, and they are all 3 going to be very small. All right, so T1 is going to start, this is our schedule, and it's going to do a read of the variable X. There's one variable here. All right, then I'll do T2 is going to come in and it's going to write to X. All right, we don't even care what value it writes to X. All right, then we're going to go back to T1, which is also going to write to X. Again, it doesn't matter what it writes. It doesn't matter for this. And then we'll have our final transaction, T3, which also writes to X. A bit of a strange schedule. We read X and then 3 writes, but okay. Now, we can look at the conflict graph for this. All right, we're going to have 3 nodes, right? T1, T2, and T3. So this is also just a good exercise in figuring out conflicts, figuring out the conflict graph, right? Here's how I do it when I'm faced with just a schedule like this, right? I'm going to look at this first line, okay? T1 does a read of X. That's going to conflict with any write of X, right? Any write of X that comes after it. So this read of X and this write of X gives us a line from T1 to T2. This write of X gives us a line from T1 to T3, right? Then I move to the next line. Oh, I didn't mean to erase all my arrows, right? So then, okay, this write of X on T2, that's going to conflict with any subsequent operation on X, right? So in particular, T1's write of X, T3's write of X, right? And then, keep going. We already found this conflict between T1 and T3, and then we're at the end of the schedule. So we have this conflict graph here, a little bit more exciting than what we've been doing, 3 transactions instead of 2. There's a cycle in it, right? But looking at this schedule, gosh, is there anything wrong with it, right? This schedule is so similar to if we had just run T1 and then T2 and then T3, right? The final state is the same. T3's write is the last thing to happen. Even the order of the reads is the same. There's only one read. It happens at the beginning, right? But this isn't conflict serializable. We would not allow this schedule, right? This type of schedule conforms to a different type of serializability, right? It's known as view serializability. We don't need to define it precisely in this class informally, which means that the final written state and the intermediate reads are the same as in some sequential schedule. So, why didn't we go with this one? This seems a little bit nicer. We kind of found a schedule that is allowed here, but isn't allowed in conflict serializability, which, means we're a little bit constrained. This type of serializability, it's really hard to check for, right? It is NP hard to check for this. Conflict serializability is a lot more practical. It's easier for us to generate conflict serializable schedules. Schedules like this, even though they kind of make sense, are also a little bit weird. We have a lot of these blind writes. They're writes that don't get read. All right. There are a lot of other options though. View serializability. There is read committed isolation, snapshot isolation. You'll get to play around with some of these in hands-ons in the future. The most important thing to understand here, we have a ton of trade-offs between performance and sort of how difficult it is to reason about the semantics of isolation, right? There is no one best option, right? Conflict serializability, it's nice in many ways, but we can relax it further. We'll get better performance. It'll get a little bit harder to reason about the semantics, but some systems are okay with that, right? That's not always a bad thing. But for us in lecture, here's where we have ended up. We are going to think about systems that have this conflict serializability. So we are going to assume that our transactions are using 2-phase locking. That's how we're getting the schedules, right? So now we have this guarantee that, when we run things concurrently, it is as if we ran them in sequence. Helps us reason about concurrency when things don't fail, helps us reason about concurrency when things do fail. All right, so this is the end. This is the end of this lecture. It's also the end of us thinking about a single machine, right? So next week, we're going to start thinking about, well, what if we want to store data across multiple machines? And what if we want transactions to access multiple machines? All right, so that's where we're going to start next week. Also, I will put a music video for you on Piazza after this that you may enjoy and is relevant to today's lecture. All right, so that is the end of two-phase locking, and I will see you all back on Monday. I'll be here if you have questions.